Welcome to this video tutorial about RHRV, R heart rate variability. This video tutorial covers the nonlinear heart rate variability analysis of our toolkit. If you are interested in an introductory tutorial about RHRV, you may check another video tutorials in this YouTube channel, or you may go to the RHRV website. You'll find a link to the website in the description of this video. In this tutorial, we'll work with the nonlinear functionality of RHRV. We're going to use two sample files with RR intervals that you can download from our website. The first one is the nonlinear HV bits. The first thing we're going to do is set the working directory in R to the directory where I have those two files, and then we're going to load the RHRV library. Then, as always, when we work with RHRV, we create the data structure with all the results of the analysis are going to be stored, and we set a verbose mode in this data structure. This will produce a more verbose output in the console, and it will be useful to understand what's going on through this tutorial. And now we load that nonlinear HV file. The nonlinear HV file contains 5001 bits which have been artificially generated by simulating a nonlinear process. Therefore, we know for sure that the RR intervals we are loading here, they come from a nonlinear process. We build a non-interpolated heart rate, and we must create the nonlinear data structure, which is going to be a data structure within the RHRV main data structure. This data structure will store the results of the nonlinear analysis. In our PDF documentation, we have information about the data structure of RHRV. It has three main parts. This part over here is about the data we are loading, the RR intervals, the heart rate, and some episodes which belong to different physiological episodes of interest. Maybe some pathology or some test was performed to the patient during those episodes. And then we have another three data structures. One which contains the time domain analysis parameters, another which contains the frequency domain analysis parameters, and the last one contains the nonlinear analysis parameter. In the RHRV PDF documentation, you have detailed information about all the fields of these data structures. The first thing we should do when we are working, when we want to apply a nonlinear analysis, is to check if our data is really nonlinear. In order to do so, RHRV has the nonlinearity test function, which checks the hypothesis that the data was generated by different linear processes, such as an autoregressive process, an ARIMA process, and different others. In the PDF documentation, you have information about the concrete test we are performing. Here you can see that the p-values of these half a dozen tests we have conducted using these functions, they are all 0, but one which is pretty much 0 also. This is nice because this data, we know it comes from a nonlinear process that has been simulated. So we can reject the hypothesis that the data comes from the different linear processes we are checking against through these tests. A second type of nonlinearity test are the surrogate test. The surrogate test, what they do is they generate some surrogate data which has the similar properties as the original data, similar linear properties such as the mean or such as the standard deviation, but it has it's being generated through a linear process. Therefore, the surrogate data, we know for sure that it is linear. Concretely, we generate the surrogate data by presenting Gaussian inputs to a linear stochastic process. What we do here is we apply A certain function, in this case, is a function which is called time reversibility, although you may use any function of your choosing. This function measures the asymmetry of a time series under time reversal. This tau parameter is one parameter, is a delay parameter using this function. So what we don't want to do here is to check these statistics, which is a statistic which measures nonlinearity, the time reversibility statistics, in the surrogate data, which we want to test if it is nonlinear, and in the surrogate data that we know it is linear. And here we can see the values of the statistics for the original data and all the surrogates. And we can see the value for the surrogate data is much different. All the surrogates have much different values than the real data. This provides additional evidence that this data indeed is nonlinear. And that's what RHRB is saying in the console. Again, we have rejected the hypothesis that this data may come from some linear stochastic process. Now we need to calculate the parameters to reconstruct the phase space through the Takens theorem. So we need the delay and the embedding dimension. We can calculate the time delay using the calculate time lag function in RHRB. This function calculates the autocorrelation of the time series, and then it uses different criteria that can be specified by the user, such as look for the first minimum in the autocorrelation function, look for the first point where the value of the autocorrelation falls to e raised to the power of -1, or look for the first zero, and that will be the time lag we're going to use. Here you can see that the autocorrelation function falls really fast, and the time lag that RHRB has selected is just 1. Once we have the time lag, we can calculate the embedding dimension. We're gonna calculate multiple embedding dimensions and see when the correlation zoom saturates. And the maximum dimension we're gonna try is 15, and we're gonna use 10,000 points of the data series to calculate the embedding dimension. You may use all the points, but we provide the facility of limiting the number of points because these calculations can be quite CPO intensive. So we perform the calculations. We are using the cow algorithm to find the proper embedding dimension. The cow algorithm computes two time series, ED1 and ED2. The ED1 time series should reach a value equals to 1 and stay at 1 when proper phase space reconstruction has been achieved. This seems to happen here for a value of the embedding dimension equals to 5. And ED2 is a function which should take a value equals to 1 if the data is stochastic, and different from 1 if it's deterministic. Here is different from 1, so embedding dimension should be 5, and this provides additional evidence that this data is nonlinear. We can check the embedding dimension that has been selected by the function. Oops, I erased everything. We're going to check the embedding dimension is 5. And now we can start calculating nonlinear statistics. The first nonlinear statistic is going to be the correlation dimension, which quantifies the dimensionality of the reconstructed phase space. We're going to use multiple embedding dimension. This is always recommended when you are computing a nonlinear statistic, because once proper phase space reconstruction has been achieved, using a higher embedding dimension should return the same value for the statistic. We want to use a radius for finding points in the phase space which are close to each other, starting it at 1 the radius and going up to 100 using 100 different radiuses. So we're gonna try with the radius equals 1 millisecond, 2 milliseconds, 3 milliseconds, up to 100. And when we look for points we are close to each other in the phase space, we are gonna ignore those points which are close to each other, but they correspond to points in the temporal domain which are at 20 samples, 20 heartbeats from each other. Therefore, we are not considering those points which are close in the phase space because there are temporal correlation between themselves. We only care about those points which are real recurrence, where the trajectory of the phase space has returned to a point very close to the original one after some time, and not just because there are temporal correlation in the time series. So we calculate the correlation dimension for different values. The doPlot parameter means it's not going to plot the value. We could have set the doPlot parameter to true, and then we will have a void to use the plot correlation dimension function. Here we can see the logarithm of the correlation sum plot against the logarithm of the radius, and we can see that we find a very nice linear behavior for most of the radius. When the radius starts to be very big, then that linear behavior is broken because we are seeing a radius which is far too big. And these lines have the same slope, they are parallel lines. This is what you expect to see. You have achieved proper phase space reconstruction. And here we show the slope of these lines, and we can see that the slope is quite stable from approximately 1.5 to 10. So we're going to use these values of radius starting in 1.5 up to 10 to reconstruct the estimate the correlation dimension. So the regression dimension, the regression range from the calculation of the correlation dimension is going to be from 1.5 to 10. And we're going to use all the embedding dimensions. The library has averaged the estimation of the correlation dimension for all the embedding dimension, and the average value is 1.8. Now we're going to compute the sample entropy, which measures the complexity of the time series being measured. We provide pretty much the same parameters. In this case, we are going to use higher embedding dimensions, so we have to recompute the correlation dimension because we will be obtaining more reliable estimation of the sample entropy if we use higher values for the embedding dimension. So we recompute correlation dimension for higher values, and now we calculate the sample entropy and we plot it. And in the plot we see that from approximately 5 up to 20 we have more or less flat region. This should be the region we should use for the calculation of the sample entropy. So we're going to use the region, well, the one which has been specified here is from 10 to 20. So we're going to compute it. Here in this plot we show with the horizontal lines the different values for the sample entropy for each of the embedding dimensions. And here we see in the console the numerical values. They all the values are around 0.3, 0.31 more or less. The fact that those values are quite similar to each other provides evidence that indeed we are analyzing some data which has nonlinear structure. We're going to reset some graphical parameters in RHRB, and now we're going to calculate the maximum Lyapunov exponent, which quantifies the rate of divergence of closed trajectories in the phase space. In this case we are using a radius of 3, and we can see here the plot from which we should find here a linear region to perform the linear fitting whose slope is going to be the Lyapunov exponent. The linear fitting should probably be performed from 1 to 5, 6. So we're going to estimate the Lyapunov exponent using that range of values. And we see that the estimation gives a value, the Lyapunov exponent of 0.46. Next we're going to calculate the D-term fluctuation analysis, which quantifies the presence of fractal correlation properties in the data. We're gonna use windows for this calculation, starting in 6 milliseconds, going up to 300 milliseconds, and we'll use 25 windows in that interval. We must again look for the proper linear region to perform the linear fitting to estimate the first scaling exponent, which will be from approximately 20 to 100, for example. As you can see, all the nonlinear functions have the same structure. First, you compute some values with a calculate something function. You should plot those values. You should find the proper linear region to perform the linear regression to calculate that statistic. And now we're going to calculate it by performing a linear regression from 20 to 100 for values of radius from 20 to 100, or values of the window in this case. We're going to perform recurrence quantification analysis. This recurrence quantification analysis is a tool to quantify the number and duration of recurrence in the time series in its phase space, and there are multiple statistics which can be computed in order to do so. You have a complete listing of all the statistics we calculate in the PDF documentation. They are, for example, the percentage of recurrence points in the recurrence plot, or the percentage of points that form a diagonal line, or the length of the longest diagonal line, and they are standard parameters to characterize the recurrence plot. Here we have finally the recurrence plot. It took some time because it's quite CPU intensive to perform these calculations. If we check the data structure, we can see the names of all the different parameters that have been computed to characterize this recurrence analysis, and we can access one. For example, this will be the Shannon entropy of the diagonal line length distribution. And now we're gonna reset the analysis. We're going to create again an RHRB data structure and discard the former one, and we're gonna load some real RR intervals from a real electrocardiogram recording, which should belong to a healthy subject. It's my electrocardiogram, so I think I'm healthy. So this should be a healthy patient. We're going to create the nonlinear analysis data structure. Again, we're going to set it to verbose. And the first thing we're going to do is check for the nonlinearity in this data. We check it and we see that all the values are close to 0, which is meant, again, does not really mean that our data is nonlinear. It means they were not generated by the linear process against which we are comparing our data. They were not generated by some R or ARIMA process, for example. And if we apply the surrogate test, in this case things are not that clear. In this case, the real RR intervals have a value which is similar to some order of the surrogate data. We know that the surrogate data has been generated by a linear process. So the surrogate data test tells us we cannot reject the null hypothesis. We cannot reject that this data is linear instead of non-linear. Should we go ahead with the analysis? Some authors which apply non-linear techniques to the analysis of heart rate variability won't even test for non-linearity, and they just compute the statistics. In that case, the statistics, if the data turns out to be nonlinear, they lack of physical interpretation. They are still a reproducible set of mathematical operations that you are applying to your data. And maybe if you apply the same operations to the different populations, you may find statistically significant differences between the populations, and therefore maybe you can use that number to distinguish between the two populations. But you cannot say, for example, that if you are working with some data which it is linear, that you have calculated a maximum Lyapunov exponent that gives you any idea about the rate of divergences of closed trajectories in the phase space. It's just a number which may help you distinguish the two populations. Here we're going to go ahead, we're going to calculate the time delay for the Jenkins reconstruction. We use the first minimum of the autocorrelation function, and the time lag is 2, and then we're going to calculate the embedding dimension. And again, we see here that we reconstruct the phase space properly since for a value of embedding dimension of 12, but you can see that in this case ED2 is very close to 1 for pretty much all the values. And this is telling us that we cannot reject the hypothesis that this data was really generated by some stochastic process instead of a nonlinear process. Now we're going to apply some nonlinear filtering, nonlinear noise reduction techniques to the data. This is very important if your electrocardiogram comes from, if your electrocardiogram has been sampled at a coarse frequency, for example 200 Hz, 100 Hz. This means that you have a very big discretization step for the RR intervals. If your electrocardiogram has been sampled at 100 Hz, your discretization step is 10 milliseconds. This big discretization step can, in a time series, break its nonlinear structure, even when this linear structure is really present in the data. If we are discretizing it very coarsely, we may break it. The nonlinear noise reduction algorithm that we have implemented in RHRB is going to add some random noise to each of our original data points with a value equals to the discretization step, with a value which pretty much ranges from 0.5 / the sampling frequency plus minus that value. And then after adding that random value is going to apply a nonlinear noise reduction technique. We're going to do that. This is a little bit controversial. After doing this, I'm going to check again for nonlinearity. The nonlinear test pretty much gives me the same values as before, but the surrogate test this time is telling me that the original statistic, the statistic coming from the original data and the surrogates have different values for the statistic. This could mean two different things. One thing is that we filtered noise in the original data and we managed to recover the nonlinear data structure. That would be great. The second thing, it could be that we started with some linear data, and by applying this statistic we created some fake nonlinear structure which is being picked up by the surrogate test. The application on the noise reduction technique is definitely necessary if you have an electrocardiogram which has been coarsely discretized, but this is controversial, however, in the nonlinear analysis literature, because some authors claim that you may be creating some fake nonlinear structure in your data. We're going to go ahead and we're going to plot a Poincare plot. It's a nonlinear analysis technique that we did not cover in the first part of this tutorial. Here we are representing one RR interval and the next one in two different axes. This plot is usually characterized by the two axes of ellipsis, where the axis which is perpendicular to the identity line characterizes short-term variability in the patient, and the axis which is parallel to the identity line characterizes long-term variability. And finally, we're going to calculate a correlation dimension for this recording, and we're going to plot it we see that the values for which the correlation sum is parallel, they are probably from like 60 to 100, more or less from 60 to 100. This is more or less flat. So this is the regression range we could use to compute the correlation dimension, and we obtain a value of correlation dimension of 7.979. Again, it could be arguable if this has any physical interpretation. Correlation dimension usually quantifies the dimensionality of the reconstructed phase space, but we may be in the case that we are analyzing some stochastic data and there is no really attractor in the phase space. We are obtaining this value because we applied the nonlinear reduction algorithm and we created some fake structure. Well, this is everything we have prepared for this tutorial. If you want more information about RHRB, we strongly encourage you to go to our website. We have a documentation section where you can find other videos and our PDF tutorial where you can download the sample files used in this tutorial and in other tutorials. And we also encourage you, if you like the project, to contribute. RHRB is an open source project, so any contributions are welcome. Thank you for watching this video tutorial.